Hey, welcome back to this Python tutorial. In this tutorial, we'll be learning about semantic similarity of text. We'll take a very simple use case, and as usual, we'll code it from scratch. The use case that I have right now is I have a list of queries. I'll call each of these sentences independent queries. Now, this is a set of 20 queries. I want to input a new sentence and see which of these 20 is the closest match to that sentence. So already the database exists for these 20. I have loaded it into an Excel. Now, just to show it to you, it's here. Imagine a new statement coming in, and our task is to find that semantically which of these 20 statements is the closest to our new statement, or to take it one step further, which are the top 5 closest statements, top 10 closest statements out of these which are closest to a new one. Now, what can be the possible use case for this? Maybe you have a lot of data and very little capacity to process. So you can take the top 15, 20, 10%, whatever number that you choose, that top 10% data for further processing. So you can ignore the rest 90% just by using semantic similarity. That's one use case. You can further process that data, you can further process those 5-10 statements instead of taking the entire cohort of these 20 statements. Now imagine it can be 20,000 statements and you pick up the first 1,000 statements. So that's top 5%. That's a reduction in processing time of 95% simply by implementing this model. So the applications can be huge. This is to give you a clear glance of the data that I'll be using. This is a random set of statements that I generated off the internet. You can add thousands to these and see the results. Before we start, what we usually do is see the version that we have, see if we've installed Python that's using the first statement. We create a virtual environment if not already done. Since I have a virtual environment, I'll simply use the third statement to activate it. And this is how my virtual environment is activated. Import the necessary libraries. We'll use the Hugging Face model. This is the open source Hugging Face model that we'll use. This is very simple because the sentence transformers class hides a lot of complexities and it's good for our use case. We need not delve into the nitty-gritties of it and can simply harness the power of this LLM. The installations that you see commented out will be used in case you don't have them installed already. In that case, you can use this. Although we are nowhere exclusively using OpenPyXL, you will need to install it because eventually Python will give you an error. The first time you run this model, it will take a while longer. It will install more things, 5-6 other things, but the next time you do it, it won't do those installations again. I've imported pandas, NumPy from sentence transformers, imported sentence transformer, imported the FAISS. So this is Facebook's AI similarity search. It acts as an index and a database for us to store our embeddings, something that we will be using shortly. So the idea is to very simply in raw terms, for every statement that you see here, for example, let's take the first statement. So for the first statement, what we'll do is we will convert this into a number such that it's converted into a vector. So this sentence will be transformed into a vectorized state. The vectorized state would be a vector of 384 dimensions. That is the number of dimensions our model, the one that we're taking, supports. So imagine this sentence being converted into a matrix which would be looking like this, and it will have 384 dimensions or 384 columns. So until n 384. each of these columns will have a number associated with it, and that number will encode. We'll not be able to interpret it, but that number will hold the semantic meaning, similarity, as well as reference of the statement. This matrix of 384 dimensions will hold this sentence and have a number in each of the columns that it has. Similarly, the second line will be converted again into a dimension of 384 columns. Eventually, with all of these 20 lines of sentences, you will get a 20 row cross 384 columns matrix. So you'll get a 20 cross 384 dimensional matrix. This matrix would store your entire input data. What will happen next is that your input prompt, which will again be a single statement just like any of these above, that would again be converted into a matrix of 1 cross 384. That's similar to what we've done. So each of these is a 1 cross 384, 1 cross 384, all of these. That's why, and that's how they combine into a 20 cross 384. After calculating this, so each row will, in this entire framework, each row would be independent of each other. Then for each row, you remember to calculate the distance between 2 points, say x comma y, or x1 comma y1 and x2 comma y2, we use the Euclidean distance formula. That's under root of x1 minus x2 whole square plus y1 minus y2 the whole square. So the similar or same formula will be used for this 384 dimensions. This was the calculation for 2 dimensions, but imagine doing that calculation for 384 dimensions. So x3 comma y3 and x4 comma y4 continued up till x34 comma y34, where x is your each of these statements one by one. So in one instance, this would be x, then this would be x, then this would be x, then this would be x. So 4 calculations like these, and so on. And your y would be constant. It would be that same 1 cross 384 vector, which would be the new prompt that the user inputs. So we'll get more clarity as we move on. Let's start with the code after getting this brief idea. So just keep in mind that this would be a 384 dimensional matrix. After loading these libraries, you see that the model is also initiated. I've put the file path in a variable, the sheet name in a separate variable. I'm using an Excel, so all of the data that you saw earlier in this file, all of this is pasted as it is in an Excel. That Excel is called prompts.xlsx. It's stored in sheet 1, and I load the data here using pandas. Then I convert those prompts from which are mentioned in the query column. So that's the column name, the top one at the top. I converted it to a list. Let's start with the embeddings and vectorization of each of these prompts. So how do I vectorize it? I say embeddings array. Let me create that array and call it embeddings array. This would be model, the one that we loaded earlier, the Hugging Face model, dot encode. It will help us encode it. And what will we encode? We will encode the prompts that we specified earlier. The dimension of this matrix, this array, as I told you, is 384, and that's what we'll be seeing here. So embedding array dot shape. Actually, it's shape brackets 1, but for now, let's just try to see what that dimension is. Just holds the shape of the embeddings array. As you can see, it's a 20 cross 384 matrix. These are the number of dimensions, 384, and 20 is the number of elements or the number of prompts that we are supplying. we need the dimension of 384. So I'll just add square brackets 1 here. I'll rerun for you to see what this dimension now holds. Meanwhile, I'll start coding the next part. So after your dimensions are, or after we have the dimension as 384, I'll start by calling that index that we called earlier, that we installed earlier. So let me simply call it index is equal to FAISS dot index, and you can see multiple options here, but we'll be going with flat L2. So L2 is the Euclidean distance we talked about earlier, and we'll pass in the dimension parameter here. Simply an index or say 384 empty cells have been created in the memory, and we'll simply use the index.add to add the embeddings array to these empty cells. And with that, our index is loaded with these embeddings. So remember how we started? We had these statements, English alphabets joined together. These English alphabets were converted into a 384 dimensional vector using the model, using this model. And where is that happening? It's happening here when we are calling model.encode. Then after encoding, we are storing all of this data using the FAISS index. And we've specified that we'll be using L2 or the Euclidean distance to match. Our model is ready. Let's use new underscore prompt to call the new prompt. And let's say it's a very general statement like, how is the weather today? Then I'll also have to create an embedding for this prompt because it's still in English. So for the model to understand, we'll use the same code that we did above. So it's model.encode. And what do we want to encode? We want to encode the new prompt. There's one additional argument, an argument which we didn't use above, that's called convert to tensor. So you can see convert to tensor and you make this true here. You can learn more about it, but the idea is that first tensors are more suitable for embeddings and these frameworks. So we'll first be converting into a tensor to store, and then eventually when we use it, when we use the new prompt, we'll convert it back into a numpy array. Here also, we would have ideally said convert to tensor is equal to true, and then here passed a statement that hey, convert this embedding array into a numpy array and then store it in the index. But that's what's happening in the background. So we'll not fiddle with that. Let's say k is my parameter, which is the top similar statements I want. So it can be anything. Let's say I want top 10 similar statements, top 20 similar statements. For now, since we are dealing with a small data set, I'll say that we want the top 3 similar statements to our data set. Then we'll use distances comma indices is equal to index.search. So this is where we are searching our new statement in our database. That database is now stored, that data is now stored in the index variable. And remember, index is an FAISS index object. And what do we want to search? As I said earlier, we'll be converting the new prompt into a numpy array. So numpy array, what do you want to convert into a numpy array? We'll want to convert the new underscore embedding. We'll also be passing the parameter k here. So we want to search this in our index, in our database, and retrieve the top 3 statements. Then let's say we print the L2 distances, the Euclidean distances. The Euclidean distances would be distances. It's stored in the variable called distances. Similarly, let me also print the indices. Print open bracket indices. These indices are the order in which the data is stored. and we can see it in the Excel as well shortly. Then let's print the three responses that are closest to our new prompt. So we'll say for I, that's our classic variable. For I in range, what is the range? We want the top three. So let me call it K only for now, because K stores the variable, stores the number three. And I'll simply say print. What do I want to print? I want to print F. I'll use the F string here, and I'll say the top closest prompt is, comma, prompts. This prompt stores the Excel. Remember, we stored the Excel data in this variable called prompts. We're calling it here again prompts, and we'll use the indices variable. You will shortly see how. Why? Because now we are printing it here. With that, you'll get more clarity. We'll use the 0th row because it's a single row object. It's actually a matrix with one row and k columns. So it's 1 cross k in dimension. K is 3 in our case. So it's a 1 cross 3 matrix. I'll show you shortly. We've completed coding the entire thing. It's time to run it now. Let's give it a second. So the file must be getting loaded, the embeddings must be getting created and stored. Then the new prompt is being read, then being encoded, and then being searched. Then the relevant distances and their indices being calculated. These are the relevant distances. By experience, I can tell you these are huge distances. So our prompt is not very close to any of the prompts that are in our dataset, but these are the closest ones according to the semantic match that the model was able to do. So for example, we said, how is the weather today? It's relating clouds. That's one catch variable. Then enjoy the park, warmth of the late afternoon. This is also somewhat related to the weather, and maybe winds here is related to the weather. You can see the distances are huge, but that's the closest that we've got. The second, again, try to observe this where you see that it's a matrix. It's a 1 cross 3 matrix. It's a matrix. It's two-dimensional, 0 cross k. You have indices 1, 4, and 2. So our indices 1 would be, so okay, before that you see top 0, top 1, top 2. That's not very appealing. Let's say I plus 1 because Python starts its indices at 0, but humans start at 1. So I'll just put in an I plus 1 here. We got 1, 4, and 2 as the indices. So let's go back and see clouds drift lazy. So 0 is the first line, second line, or 1 in our case. This is 0 and this is 1. So clouds drift right. This is the first index, then 4. So 0, 1, 2, 3, 4. People gather in the park. As you can see, that's the second most closest statement. And then 2. So 0, 1, 2, the sound of birds. That's the third closest statement. With this, we saw how we can create a model which gives us the closest statement to our new prompt from the existing database. I'll build on top of this model in the coming videos where we'll automate a lot of things when we'll store this entire data into the FAISS object, and we'll not even need the Excel to be loaded every time. But that's in the future videos to come. I hope you join me then, and I'll see you soon.